yeah, today we're going to talk about differentiability, which is this topic we've been talking about all year. We have lots of derivative rules. You guys know how to find derivatives, and we even know a few applications of derivatives like L'Hopital's rule, and something that we'll come back to, position, velocity, acceleration. Right? Those are really the main two applications that we've seen so far, aside from just being able to find slope and rate of change of curves that are not linear. But what we're going to talk about today is kind of just take a step back and talk about like how to know if your function is even differentiable in the first place. Like we want to be able to tell just at a glance whether or not we can actually differentiate the function. And so today we're going to revisit a topic from Unit 1 and talk a little bit about continuity of a function and how that's related to the differentiability of a function. So a function is considered differentiable if you can find the derivative. Yeah, if you can find the derivative at a certain point, then it's differentiable at that point. And if a function is differentiable across its domain, then the function as a whole is considered differentiable. This is kind of similar to the idea of continuity, where you can have a function that is continuous on its domain, but you could also have a function that has discontinuities that's still continuous, like on certain intervals. And one of the things that we looked at the beginning of the year was trying to decide, like, when was a function not continuous? And also talked about different discontinuities and classified them. Okay, now, for a derivative to exist, you have to be able to find the slope of the line that's tangent to that curve. That means there's a couple of different curves that would not be differentiable because you cannot find the slope. For instance, if you have a vertical tangent line that has an undefined slope, the function would be considered not differentiable there. Okay, but I really want to make sure you understand that there is a difference between being differentiable and being continuous. Okay, there's since you have to be able to find the slope at a given point for it to be differentiable, we can rest assured that if it's differentiable, it is continuous. Okay, differentiability implies continuity. This is a really important point to make. Okay, I made sure to, on our website, post a link to a proof of this. Okay, it's actually pretty short proof. The video is just 2 minutes long. But if you want to see, for sure, that if a function is differentiable, then it's continuous, you can check that out. But the reverse is not true. Okay, continuity does not imply differentiability. In other words, just because a function is continuous doesn't mean you can find the slope everywhere. So just take a minute and see if you can come up with a graph. It doesn't have to be super detailed or anything. Just imagine in your head and maybe jot it down here. Try to draw the sketch of a function, just any graph, that's continuous but not differentiable everywhere. Okay, maybe it's differentiable some places, but that has some point where it's not differentiable. Just take 10 seconds here, throw something down. Doesn't have to be super detailed or anything, but I just want you to start to be thinking about the difference between being differentiable and being continuous. Now, in order for it to be continuous, you have to be able to sketch the curve that you just did without lifting your pen. Okay, so if whatever you have drawn requires that you lifted up your pencil, then that's not going to be continuous. All right. So what kind of graphs do y'all have down here? I don't know. Anyone want to share what they have?
I have just a very steep line.
A steep line, okay?
Very steep.
So
Practically zero.
practically zero.
Or infinity.
Okay, so it's going up like this.
No, like an exponential line that's just going very straight up.
Okay. So that now we want to be careful here because an exponential function is not going to have a vertical tangent line. But you're saying you have now, unfortunately, if you actually have a section that is vertical, that can't be a function.
Yeah, but if it's not, it's very, very close.
Well,
it looks like it's almost vertical.
yeah, but then the slope's not going to be undefined then, and it's going to have some kind of slope there. The only way to get that that undefined slope is if it's only vertical at a single point. In other words, like if your graph does something like this, where like at a single point we have a vertical tangent line. So something like that could work. Another thing, yeah, anyone else have, what do you got over here?
I did zigzags.
A zigzag, yeah, something like this would definitely work. Okay, any sharp corner is a point where the function is not going to be differentiable. Okay, I think kind of the classic example here of a function that's continuous but not differentiable is just the absolute value of x. Okay, it's kind of a real basic one where the graph does something like this, right? Where we cannot calculate the slope of a tangent line at x equals 0. And we'll get in a little bit more detail on why that is. But so yeah, basically, how do we know if a function is differentiable? Well, we want to look at the graph and look for these behaviors to say, oh, it's not differentiable. So in other words, if you have a corner or a cusp, as sometimes it's known, this would be an example of where it's not differentiable, but it is continuous. So this is continuous, but not differentiable. Now, if you're trying to sometimes it's not so obvious. Like, what if the slopes are what if the corner is not so clear that it's a corner? What you really want to be looking for the differentiability is like right around that point where you think maybe it might not be differentiable. Like right here, if we check the slope like right barely to the left of it, and the slope right barely to the right of it, those slopes are not going to be equal, right? This one's pretty obvious, right? One's positive, one's negative. You don't even have to figure out what the numbers are. But if those slopes like on either side, in other words, as the limit as x approaches that number, if we check the slopes as we get closer and closer to that x value, those slopes should converge on each other. So that like right barely to the left and right barely to the right, we have slopes that are the same. Okay, so like these slopes are definitely not equal.
So a sudden automatic change, basically.
Exactly. If the slope like suddenly changes from like even if it's like 3.1 to 3.6 or something like that, then that's going to be a point where the function's not differentiable. Now, there's not really like a point that you want to be checking. We'll have to like use limits to actually check that, but we'll get to all that. Okay, if a function has a discontinuity. We lost the screen here. Hold up. Let's bring that back up. All right, I think we're back. Okay, good. So if a function has a discontinuity, it will not be differentiable. Okay, so if you have a point where it's not continuous, then it's not going to be differentiable. Okay, this is actually what's known as the contrapositive of the statement differentiability implies continuity. So what I'm saying is, if a function is differentiable, then we can say it's continuous. You don't need to know the word contrapositive, but basically what it's saying is, if it's not continuous, then it's not differentiable. And those are logically equivalent statements. Those two statements mean the same thing. So those are a couple of examples. The last example that you might run into, this is a case where the function is continuous but not differentiable, is when you have a vertical tangent line. So as we look at graphs and we're trying to determine whether or not a function is continuous or differentiable, these are the kind of things we're going to be looking for. So we'll go through a few examples where we look at graphs, and then we'll do a couple of examples where we look at equations and see how we can tell. Any questions so far? Okay, I'll give you a second to finish writing that down. All right, number 1. It says, for which values between -9 and 9 exclusive, so not including the endpoints, and on the AP test, you're pretty much never going to be asked about the endpoints unless it's an absolute value, or I'm sorry, an absolute max, absolute extrema question. That's not what we're dealing with here. So for what values on the interval is the function discontinuous? So this is kind of a review from Unit 1, but the different types of discontinuities we have are removable and non-removable. So maybe I'll write up here, removable discontinuities are where the limit exists, okay? And typically these are going to occur at locations where we have a hole, all right? Either just a straight up hole, or even if you have a hole and the function's defined elsewhere, both of those scenarios are more or less classified in the same category here. They're both removable. Okay, non-removable discontinuities are where the limit doesn't exist. And there's 2 different types of discontinuities that you'll see, one of which is a jump, where we have like a piecewise function. Let me kind of separate this a little bit. Should have given us a little bit more room here, where you have like 2 pieces that are not connected. Okay, the other type of non-removable discontinuity is when we have an asymptote. So something like this, a vertical asymptote. We can call that either an infinite discontinuity or just call it a vertical asymptote. All right, so looking at that first graph, we're basically going to read it left to right and looking for any place where if you were to sketch the graph, you'd have to pick up your pencil. And so the first time that happens is right here at -5. Okay, so we have a discontinuity at -5. We'll say, we've got one at x equals -5. And is that going to be removable or non-removable?
Removable.
Yeah, removable. And a little bit more specifically, it's a hole. Yeah. Okay, the next discontinuity is at -3. Okay, what kind of discontinuity do we have there? Yeah, non-removable. Okay, because we have a jump. All right. Where's the next discontinuity?
0.
0. Yeah.
Removable.
That's going to be removable. That's a hole. And looks like there's just one more. Yeah, we got one at 5. And what's going on at 5? Can't try the straight one. Yeah, we've got a vertical asymptote. Yeah, so that's going to be a non-removable discontinuity. The limit does not exist there. And yeah, we'll call it an infinite discontinuity. Okay. Yeah, you can call it either one. Yeah. Either way's fine. Okay, so that's all the review. We did that back in Unit 1. Yeah. Number 2, determine all the values where f of x is not differentiable. This is different than asking whether or not it's continuous. So where would it be not differentiable? Where's the first place where we see either a a corner, a discontinuity, or a vertical tangent line?
It's -3, or would that be differentiable?
Which where? Say that again.
-9, like at the point.
So we're not going to look at the endpoints. This is going to be exclusive. So yeah, ignore the where.
-3.
Okay, so -3. What's happening at -3?
Automatic change.
Yeah. So yeah, we've got basically a sharp corner there. Okay, so at x equals 3, we've got a corner, or a sharp turn, sometimes it's called.
Could we say -7?
Okay, very good. -7. What's happening at -7?
0.
It's a vertical tangent line.
And at 2.
Okay, yeah, that's also happening at 2. Very good. So we have another vertical tangent at 2. Okay. And anything else? 6. Okay, why is it not differentiable at 6? Yeah, you've got a discontinuity there.
Oh, I thought it was only for jump discontinuities.
All discontinuities. Yeah. Am I spelling this right? Discontinuity. All right. So any questions about how to identify visually points where the function is either continuous, not continuous, differentiable, or not differentiable? The differentiability question is like, can I find the slope there? Is there a slope there?
3 is only answer x equals 1.
So yeah, number 3, it says find where it's continuous but not differentiable. So you're right. The only location where that's happening is at 1. Okay, we have a sharp turn there. Any questions about that one? I think we'll be okay. Number 4. Okay, so now we're going to determine whether or not these piecewise functions are either differentiable or continuous at the point where we're switching from one function to the next. Now, this is something we've done before for continuity. Right? How did we determine if the function, like for number 4, how would we determine if this was continuous at x equals 3? How do we know if like these two pieces like match up together? That's exactly right. Okay. So to determine if they're continuous, we're going to check if both pieces are equal at x equals 3. Okay, so we're going to check to see what the value is at x equals 3. And if they're equal, then we'll know it's continuous.
Can you derive the slope?
All right, we'll get there. We'll get there. So let's check the continuity. So we're just going to check. We're going to evaluate each one at x equals 3 and see if they're the same. So 3 squared minus 3 times 3 minus 2. That'd be 9 minus 9 minus 2 is negative 2. And then if I plug in 3 to the second equation, we get 3 times 3 minus 11. So 9 minus 11 is also negative 2. So since these two numbers are the same, since the left-hand side equals the right-hand side at 3, we can say that, yes, it's continuous. Now, in order for it to be differentiable, we're going to do a similar thing here, where we're going to check the left and the right-hand side. But instead of checking the value of the function, we're going to check the value of the slope. Because what has to happen in order for it to be differentiable there, even if they're connected, we don't want there to be a sharp turn. We need the slope at that point to be the same for both pieces so that there's a smooth transition for the slopes. You can't have like just an instant change. So to check to see if they're differentiable, we're going to see if both derivatives are equal at 3. So we're going to check both derivatives at x equals 3. So what's the derivative of the first piece? 2x minus 3. So that'd be 2 times 3 minus 3, which would be 6 minus 3 is 3. All right, we'll check the second one. 3, what's the derivative of the second one? 3, and 3 equals 3. So those are the same. So we can say f of x is differentiable at x equals 3. So not only is it continuous, but it's differentiable. Now, there is a shortcut here, just so you know. Remember that differentiability implies continuity. So if we can determine that the function is differentiable at that point, we don't have to check continuity. We know it's going to be continuous there. In other words, we really didn't have to do this first step. If we just check the differentiability, we know it's continuous. Now, it's still a good idea to check both, because if it's not differentiable, you're going to have to check the continuity anyway, because just because it's not differentiable doesn't mean it's not continuous. So, yeah. All right, we're pretty much out of time here, so your homework is going to be to do problems 5 and 3, okay, 5 and 6, the next two problems. Okay. Yep, that's your homework, 5 and 6. All right, so we didn't get to these last couple of problems in class, so let's go over them now. Number 5 says determine whether the function is differentiable, continuous, both, or neither at the value where the rule for the function changes. And so the value where the function is going to change is going to be x equals 5, because when x is less than 5, we'll use x plus 7 to define the function, and when x is greater than 5, we'll use 2x plus 2. Now, we're going to check the same way that we checked the first one. But one thing I want to point out here is that this says that x is strictly less than 5, and this says x is strictly greater than 5. So that means right away we can say that it's not going to be continuous. This is going to be a little deceiving, I think. If we plug in 5 into the first equation, we get 5 plus 7 is 12. And if we plug in 5 to the second equation, we get 2 times 5 plus 2 is 12. And so you might be tempted to say that it's continuous, because at x equals 5, both of these functions have the same value, so they should touch each other. But there is no value for when x is 5, okay? Meaning like our graph is going to do something like this at that point. So because the function is not continuous, it's not going to be able to be differentiable. So it's not continuous. So maybe I'll write it like this. It's not continuous because f of x is not defined, or maybe let's be a little bit more specific. Not continuous at x equals 5. It's continuous everywhere else because f is not defined at x equals 5. Now, since it's not continuous at x equals 5, we can say right away that it's also not going to be differentiable. We can't find the slope at that point, so it's not differentiable at x equals 5. And really, we can just say because it's not continuous, because f of x is not continuous there. Okay, so remember that differentiability implies continuity. If it's differentiable, it is continuous. The reverse is not necessarily true. If it's continuous, we can't necessarily say that it's differentiable. But what we can say is the contrapositive of differentiability implies continuity, which is that if it's not continuous, then it's not differentiable at that x value. So yeah, this one is not continuous or differentiable at x equals 5. Now, number 3 is going to be a little bit more challenging here. It says determine the values of a and b that would result in the function being differentiable at x equals -3. And x equals -3 is going to be the point at which we switch over from one piece to the next piece. So to determine what the values of a and b are, we might start to, check the differentiability, or not check it, but make sure differentiable. Sorry, it's really hard to spell white talk. Well, we don't want to ask the question. We want to make sure that it's differentiable. So in order for it to be differentiable, the derivative of the one piece at x equals -3 needs to equal the derivative of the second piece when x is -3. So differentiable at x equals -3 means that the derivative of the first one, so the derivative of this, maybe I'll just write that up here, 3ax plus 3, the derivative of that is simply the slope, which is 3a. Okay. Now the derivative of the second piece, this bx squared plus x minus 8, is going to be 2 times b x plus 1. So we want those two expressions to be equal to each other to ensure the differentiability. So we're going to say 3a equals 2b, and then we're going to plug in -3 here for x plus 1. Now we're going to run into some problems if we try to solve this because we have two variables. We've got an a and a b. So let me just try to clean this up a little bit. I'll say 3a, and this will be -6b, so plus 6b equals 1. Obviously, we can't solve this. So what we also need to do is come up with another equation that we can get from knowing that if this thing is differentiable, then it's also continuous. So if it's continuous as well, that means that these two pieces need to be equal to each other, the original pieces, at x equals -3. So we'll set those equal to each other. 3 times a, and then the x is going to be -3, plus 3 equals b times -3 squared plus -3 minus 8. And simplifying this is going to give me -9a plus 3 equals 9b plus... oh, no, that's not times. That's minus. So minus 11. And then I'm going to try to pull all my variables to the left-hand side and leave the constants to the right. So I'm going to subtract 9b from both sides and subtract the 3 from both sides, so I get -14. Okay, so I've got two equations here. Both of them have an a and a b. And so what I'm going to have to do is solve this as a system of equations. So I've got two equations here, 3a plus 6b equals 1, and -9b minus 9b equals -14. And I could solve this using substitution, but I think it might be a tad bit easier to solve it with elimination. So with elimination, what we try to do is get the coefficients to one of the variables to be opposites. Looks like I miswrote that. That should be 9a. Yeah, looks like I miswrote that down here too. That should be a. Sorry. Okay, that looks a little better. Okay, so, and now we got that fixed up. Yeah, we want to multiply that top equation by 3 so that I can combine these two equations using elimination. So 3 times 3a would be 9a, 3 times 6b would be 18b, and then 3 times 1 is going to be 3. And so the system I'm actually going to solve is this one right here. If you chose to do substitution, like that will still work. But I chose to do elimination. So once you have your system set up, you can go ahead and use elimination by combining these two equations, combining the like terms. Negative 9a plus 9a is 0, and that's kind of the whole point of multiplying by this 3 here, is so that we can eliminate that variable. 18b minus 9b is going to be 9b. And then 3 minus 14 is going to be negative 11. So if I divide both sides by 9 here, I get a b value of negative 11 over 9. Now, once I get that b value, I can use that to find a. And you have a couple of different equations that you could use to find a. You can use this one over here. You could use this one. You could use any of these up here. And I think I'm going to go with this one right here. Just because should I go with that one? Yeah, I think just the doing the 18 times a fraction over 9 is just going to work out a little nicer than some of the other ones. So yeah, I'm going to substitute this value, this negative 11 over 9, into b right here, and then solve for a, right? So let's go ahead and do that. We're going to take this, put it in right here, and that'll give me 9a plus 18 times negative 11 over 9 equals 3. Now, 18 divided by 9 is 2. So really we have 2 times negative 11, should be negative 22. If I add 22 to both sides, I'm going to get 9a equals 25. And then finally, dividing both sides by a 9 is going to give me my a value, which is 25 over 9. And so now I've got a and b. So that's it for today's lesson. Sorry we couldn't get to these last 2 problems in class, but hopefully now now that we've gone over them, they should make a little bit more sense to you, hopefully. Just make sure you reach out if you're confused on either one of these. Thanks for watching.